Okay. Hello. Hi.
Now I can hear you. That's great.
So our last speaker today is Matt Young, who kindly accepted to delay a bit his lecture. And so he will continue with his second lecture on the theory of moments of L functions.
Okay, thanks. Should I still end at the same time, or should I end like 15 minutes later than originally planned?
As you feel.
Okay. Okay. So thanks. Let me share my tablet. Okay. So this is what we finished with last time. So just to kind of review briefly, so we defined L functions in general, and we wrote down a bunch of examples, and we set up all the notation about L functions, and so I finished by stating a theorem, which is the approximate functional equation. It's still written here on the slide. So we've got an L function. That's our L of Fs. We've got this holomorphic function g of u. We need some kind of bound in vertical strips. To prove the theorem, to prove the formula as stated, we only need it, let's say, bounded in vertical strips. We want it to be even, so g of negative u is g of u. We normalize it so that g of 0 is equal to 1. X is some positive parameter that we might choose. And maybe I'll say a little bit more about the role of X after we prove this. And then, so if S is sigma plus IT and sigma is between 0 and 1, then this is a formula for the L function inside the critical strip where the Dirichlet series does not converge absolutely. So it's like two sums, one with lambda f of n over n to the s, with some weight function, this v sub s function. And then we have a kind of a dual sum with the conjugate coefficients evaluated at n to the 1 minus s with a different weight function. The weight function is given by that's this v function. It's given by some kind of Mellin integral of the capital G against this ratio of gamma functions. And then there's this epsilon factor, which occurs inside the functional equation. So that's and then R is this residue term. And often the residue is 0. So this last bit was, we were just checking that this epsilon factor plays the same role as chi. And then this very last part was about a question. So I wanted to just give a proof of the approximate functional equation. And then we can start a new whiteboard and continue from there. So the proof I'm giving is just the same as in Ivanits and Kowalski's book in chapter 5. And this is like just a completely standard theorem that everybody in the subject uses quite often. So we're going to let I of f x s denote this integral. So we start with an integral 1 over 2 pi I, integral over some vertical line, let's say 3, x to the u, the completed L function, lambda of f, s plus u, g of u over u, du. So we start with this integral. What we're going to do is shift contours off to the left. We're going to pick up some poles. So if we shift this to the line, let's say -3, we'll hit a pole at u equals 0. And so that's going to give us lambda of fs. Okay, plus the same thing, same integral at the line -3, so same thing. Plus this term r, which is our residue term. So the completed L function, it may have a pole at 1 and it might have a pole at 0. If it has a pole at 1, it has a pole at 0 because of the functional equation. And so that's when s plus u is 1. which means that u is 1 minus s, and then there's also a pole at negative s. So the residue term r just accounts for that. So we're just going to leave that alone, or maybe we should just check that the residue term. Oh, I guess it's not quite right, because maybe I'll call it r prime or something, or maybe r sub lambda. So what's going to happen is this is going to give us a formula for the completed L function, and then we want to solve for the regular L function. So that means we have to divide by the gamma factors. So this r sub lambda is the residue term where we haven't yet divided by the gamma factors. So this is anyway, it's whatever you get. So this is the residue at u equals 1 minus s and negative s. And the vast majority of the time, you can just ignore this. So I don't want to pay a whole lot of attention to it. Because usually we're doing this for L functions that are entire. And then even if you do have the Riemann zeta function, which has a pole, for example, then often the residue term is still basically something you can ignore. Okay, so now we've got this integral on the line minus 3. On that line, I just want to change variables. U goes to negative u. And so, so that integral, so let's just focus on the integral here. So the integral becomes, so when you do this change of variables, I just always remember you get a minus sign in the end. It's a little slightly tricky to keep track of all the changes of sign because the orientation gets reversed and you've got the measure and everything. The du over u and all this. So here's where we're going to use that g is even. So that when we do this change of variables, we get g back, and we just get a minus sign. So it's just I don't know. So think about it. I mean, you might want to slow down a little bit and think about this, how you track down the sign, but it's not really too interesting in the end. So we just do this change of variables, and then now we're going to apply the functional equation of the completed L function. And so we get minus 1 over 2 pi I. Oh, sorry. When I changed variables, the line should go back to 3. Okay, so I shifted it to minus 3, did the change of variables. Now we're back to the line 3. So x to the minus u stays the same. And then now this should be epsilon of f, lambda of f bar, u plus 1 minus s, g of u over u du. Okay, and so rearranging, okay, so this is our, yeah, and then the point is this is our integral back, but with different parameters. So this is our integral with f replaced by f bar, x is replaced by 1 over x, and s is replaced by 1 minus s. Okay, did I get the ordering on all these parameters right? Yeah, f, x, and s, yeah. So this is the same as thing that we started with, but with some changes of these parameters. And so just rearranging it, what we've proved, or solving for the completed L function, we proved that the completed L function at s is equal to the integral I of fxs plus the integral with f bar 1 over x, 1 minus s, and then I guess minus the residue term. There's a sign error, and I bought it in Kowalski, by the way, but it's not very major deal. But anyway, it's minus the residue, not plus the residue, because we solved for the completed L function. Anyhow, so now the completed L function is q to the s over 2, and then we have our gamma function, and then it's the L function. And so then we want to solve for the L function, so we have to divide through by q to the s over 2 gamma of fs. So that's one thing. And then secondly, we want to recognize the integral as a sum. So the integral, so we can do this for f, x, and s, and then we can just substitute, you know, so for the second integral piece, it's the same structure, it's just different parameters. So what is this? Okay, so I have fxs, that's our integral. So we're just going to plug in the Dirichlet series for the L function. We're allowed to do that because we're way over on the line 3 where it converges absolutely. So we're outside of the problematic region. We're to the right of the critical strip. Okay, so what's going to happen is we're going to get a sum from 1 to infinity, lambda f of n, over n to the s, and then it's a integral. Let's see, so x to the u, 1 over n to the u, we'll have our gamma function. We'll have our q, and then it's at s plus u over 2, and then g of u du over u. Okay, and then what we really want is this integral divided by q to the s over 2 times this gamma factor, because that's right, because we're going to divide through by the q to the s over 2 and the gamma factor to solve for the L function. And so this is going to be the sum from 1 to infinity, lambda f of n over n to the s. And then just to kind of put everything together, so okay, and then I forgot to write the line of integration. It's over on 3. So it's x over n, x over n to the power u gamma f s plus u over gamma fs. The q to the s over 2 is going to cancel. We'll get q to the u over 2. So I guess I can put that in here. So whoops. Okay, I'll fix that. So I can write it as x times square root of q over n to the power u, g of u du over u. And then now this integral that we have is precisely v sub s of n over x times square root of q. Okay, so that's our kind of first piece in our approximate functional equation, and that's exactly as we claimed it was, if you go back and check. So then we also need the second piece. So we need I of f bar 1 over x, 1 minus s, and we also divide that. So this is where it might be easy to make a mistake. So you're dividing by the same factor as before. And then I guess we're also multiplying by epsilon of f. So this thing is, just to write it clearly, so this is epsilon of f, I of f bar 1 over x, 1 minus s. So I want to divide by this, like I want to multiply and divide by the same thing. So I want to divide by q to the 1 minus s over 2 gamma f bar 1 minus s. And then I have to multiply and divide by the same thing. So now I multiply by q to the 1 minus s over 2 gamma f bar 1 minus s, and then I divide by the thing I already had. So that's the q to the s over 2 gamma of fs. Maybe I'll move the epsilon of f over to the second piece. So this second piece here, this kind of correction factor, that's our epsilon of fs. If you just check the definition of that epsilon factor, that's exactly what it is. And then this term here is the same structure as the first term. But now we just have f replaced by f bar, x replaced with 1 over x, and s replaced with 1 minus s. So it's going to lead to v 1 minus s of nx over square root of q. Yeah. And I guess technically it's, now that I look at this, so the v function depends on the gamma factors, and that's buried inside the notation. But anyhow, so that's, but I guess I've got it with, yeah, the f bar. So the v, anyway, so okay, so maybe we'll if we go back to this, so the v, so this first one is the v function for f, and this one is for f bar. The second one is for f bar. So v depends on the gamma factors. So the first piece has the gamma factors for f, and the second piece has the gamma factors for f bar. A lot of the cases that we care about, those are the same. And so it's really easy to forget about this. And actually, Ivanyi and Kowalski assume that the gamma factors for F and F bar are the same. They make some assumption like this, and so they don't have to distinguish this. But just in case, you ever use this for something where they're not the same, then it's not too hard to extend it. Okay, so that's the proof of the approximate functional equation. And now I'd like to transition towards using this for something. We're going to use it to understand or to help us understand moments with alpha exams. So let's see. So let's start a new page on this notebook. So this is Tuesday. All right. Great. Okay. So yeah, and as always, please, stop me if you have any questions. So I wanted to start with some, I would call these simple bilinear form bounds. So these are some, there's more advanced bilinear form bounds that appear a lot in the subject, but the ones I'm presenting at this moment are pretty simple. Like the proofs are quite short. There's not really any advanced ideas. So, but nevertheless, they're quite useful. So let's let AN be any sequence of complex numbers. Completely arbitrary. That's part of the strength of this thing, is that we can work with completely arbitrary sequences. So then there's two versions I want to state. So the first version is the following. So it's a sum over Dirichlet characters, chi mod q. So all Dirichlet characters, not just the primitive ones. Q over the Euler phi function of q. That's my phi of q, Euler phi function. And then let's sum over these integers in an interval of length n. And look at the sum over n an chi of n squared. And then the bound is that this is at most q plus n times the L2 norm squared of the coefficients. Okay, so that's our first bound. And then our second bound is a t integral version of this. So I integrate from minus t to t. And then here I actually want, here it actually depends on where n is. So I have to take the initial sum. So the one above, it didn't really matter where it was positioned on the real line. It only mattered what the length of the interval was. But here it depends how big n is. Anyway, so you take the integral minus t to t, sum n to the minus it squared, and then this is bounded by t plus n times the sum n up to capital N an squared. So this latter bound is called the mean value theorem for Dirichlet polynomials. Okay, and so these are very general because they don't care about your coefficients, and so that's a strength because in terms of the flexibility, but it's also like a weakness in the sense that what you can get out of them is limited because of the generality. So here's one way to at least interpret these. So these say that it might be easier to first think about the discrete version where you have the Dirichlet characters. So these will say that an chi of n has sort of square root cancellation on average. Because, so here's how you might think about this is that, so imagine, think of like the ANs of size 1. So just like imagine ANs are just like random points on the unit circle in the complex plane. And then, okay, so let's say we had sum over n up to n, an chi of n. So maybe that's of size square root of n. That's like the square root sort of philosophy is that we kind of expect square root cancellation and character sums, although not always, but let's say we did, then we'd have a sum over chi mod q, and then we'd have our square root of n, quantity squared, and in total this would be basically q times n, and then you compare that to what we had, which was q plus n, times the sum over n squared, which is q plus n times n. So at least if n is smaller, or if q is bigger than n, it's this bound, the theorem, or what did I call it, proposition. So the proposition is sort of in line with or consistent with this square root philosophy. Okay, so just in this very crude sense that, if you just plugged in square root cancellation for every single chi, you get a certain bound out, and then what we're actually proving is the same as that. Now, but you can't prove square root cancellation for all of these things, so what can certainly happen is that your ANs could be perfectly correlated with one value of chi. So for example, take your favorite character chi, and then choose AN to be that chi bar of n. So then for that particular choice of chi, there's no cancellation at all. So this is kind of I don't know. So we've got like good news and bad news, or we've got like, typical square root cancellation versus like what's the atypical case, or what's the worst case scenario. So maybe worst case scenario, at least, I mean, I don't know if we should call these good or bad, or we're making some judgment on the mathematics. But anyway, so the worst case scenario, or in terms of cancellation, AN could be, let's say, psi of n for some psi mod q. And then now this bound, so the sum over chi mod q, and then you've got the sum over an chi of n squared. So this will be greater than or equal to the sum over chi equals psi. So you just take this chi equals psi, and then now with that value of an, we'll get psi bar of n, and then chi is psi. So then this will be basically n squared. And that's in line with, so the bound, I mean, okay, it has to be consistent with the bound, and then the upper bound is this one, right? The q plus n times the an squared. So this will, in this example, this will be q plus n times n. So we get the n squared term. So we have both terms. We've got like the q times n, and then we've got the n squared term. So the q times n term is kind of the typical square root cancellation term, and then the n squared term is like the worst case scenario term that you can't rule out, because you could choose your ANs to perfectly correlate with one value of chi. But then this is saying that like for the other values of chi, then you must have a lot of cancellation. Like you can't have like you can't have very many chi's where there's essentially no cancellation, because the single bad chi is already accounting for the n squared. And so if we had a whole bunch of characters where there was no cancellation, we'd have our bound would be would contradict the proposition. So or we'd get a lower bound that would contradict the proposition. So this is a way to think about these kind of bilinear form bounds. And then the T integral thing is very similar. But yeah, so I think for these lectures, I mostly want to focus on the chi aspect. But there's very much a close analogy between these two these two families. So let's give a proof of this proposition. So, okay, so what we've got is chi mod q, q over phi of q, and then we've got something absolute value squared. So let's just write that as a double sum. So we have a sum over, let's say, what did I use in my notes? M and N. And then I'll have AM, AN bar, chi M, chi N bar. And then now you just reverse the orders and use orthogonality of characters. So this is going to be Q. And then now I have M and N in the same interval, but now they're congruent mod Q. And I guess we should also assume that M and N are coprime to Q. Try to make my handwriting more clear. So this is AM, AN bar. Alrighty, and then, so I want to write this as a sum over M equals N. That's what we'll call the diagonal term, and then we'll have write that, and then we have separately the terms where M is not equal to N. And the reason for the name is like if you view this in like the M and N plane, where M equals N is this diagonal, and then we've got these other like kind of off diagonals. So when so you've got these parallel lines. So like one of these would be M equals N plus Q. The other line would be M equals N plus 2Q, etc. So the orthogonality of characters is telling us that instead of this great big like square of points that we're looking at, it's a union of lines. Because it really like kind of cuts down the dimension from like kind of a two-dimensional sum to more like a one-dimensional sum or a union of one-dimensional sums. And you have to keep track of how many one-dimensional sums you have, but that's kind of the idea. So the diagonal is very easy to control. So the diagonal is just gives you Q, sum over N, AN squared. And this is one of the terms in the bound. So this is perfectly fine. And then now the game or the remaining work is to bound the off diagonals. So for the off diagonals, it's kind of convenient to use. So I want to just plug in the triangle inequality. I want to use the simple inequality that the product of two numbers is at most the sum of squares of the two numbers. Okay. And so then if you use that, then from the off diagonals, we've got M not equal to N. We've got a Q out front. They're both in that interval. They're congruent mod Q. So they're both, and this is symmetric. So they both are going to give me, I've got two terms. They both have a factor of a half. So and they're both, because of the symmetry between M and N, I can take either one. So let's just take AM squared. So I'm using the symmetry of the problem here. And all right. So now let's take M to the outside. And then I have a sum over N. So now N is in this interval. I guess it's this one. And then N is congruent to M mod Q. And N is not equal to M. So the question is, how many integers are there in this interval? And I think it's at most Q over N. Because it's an interval of length N, we already have one integer in there. And then so then we just have to count how many extra multiples of Q can be squeezed in there. And that's just Q over N. Or did I get it backwards? N over Q? Yeah, it's backwards. Too early for me. Okay, N over Q, right? So it's N integers, but 1 over Q. We're only taking the multiples of Q, or the one over the one spaced by multiples of Q, and so there's at most N over Q in there. So usually when you count integers in an interval, there's this problem that like you could have an interval of length less than 1, but you could still have an integer in there. So usually you have to bound the number of integers in an interval by 1 plus the length of the interval. But here we already accounted for this diagonal, and so we don't the plus 1 like we don't have to worry about in this particular problem. Yeah, I've always wondered if there's a good name for this this issue of the plus 1. Doesn't seem to have like a good name in the literature that I've seen. Okay, anyhow, so we get a q, we get an n over q, and so the bound that we get is just n sum over m am squared. And that's the other term. So we've got the q and we've got the n, and then that's the proposition. So that's the proof of the proposition. So it's very simple. And then for the second one, that's the t integral one. That's the mean value theorem for Dirichlet polynomials. Here's how I would do this. So we've got our integral. So first thing I would do is smooth this out. I'd put on a bump function. So W, you could choose it to be a Gaussian, as long as it, or constant times a Gaussian or something like that. So that we just need a function that's non-negative. I want it smooth like Schwartz class, and so I want W of x to be greater than or equal to 1 for x, absolute value of x x less than or equal to 1. I want W of x greater than or equal to 0 for all x. And I want it to be Schwartz class. So this rapid decay and all its derivatives at rapid decay at infinity. Okay. So those are my properties of W. It really doesn't matter what I pick, or at least for the proof that I'm about to present, because I'm not trying to like optimize the bound very much here. So now we do the exact same thing we did before. We have a double sum. So we've got m and n up to capital M, a n bar, and then we have to integrate this thing. So we'll have an m to the it and to the minus it dt. So okay, so this is like the t integral analog of the orthogonality of Dirichlet characters property that we used for the previous result. So if you do this integral, this thing just becomes t times w hat of t. There's this 2 pi thing. Shouldn't really matter. Let's see. So maybe this is 2 pi. Probably want. Let's see. So it's e to the negative it log m over n. N over m. And I want 2 pi. Then I have to divide by 2 pi. So t is going to go to 2 pi. Yeah, okay. So it's, I guess it's like this. The 2 pi doesn't really matter. Log n over m. If I did that right. Oh, no. So this one's over 2 pi. Yeah, that one's over 2 pi. Okay, it really doesn't matter. But anyway, you get something like this. Okay, and then the idea is that this log, so we've got this t is huge, and w hat, so w is some fixed Schwartz class function, so w hat is a fixed Schwartz class function. So w hat of y is bounded by 1 plus y to the minus 2025. Oh, what year is it? 2024? Anyway, so any power you like, of course. And so basically that's going to mean that log n over m, you want to think of that as saying like approximately smaller than 1 over t. And so that's basically going to imply that n over m has to be like 1 plus big O 1 over T. And then which would imply that N minus M is less than N over T. So we're getting, so this is kind of a slightly imprecise, but nevertheless quite good heuristic that this is that this T integral is telling us that M and N are very close as real numbers, whereas previously in the other proof we had that M and N were close mod Q. So this is close in the like kind of the Archimedean sense. So yeah, all right. So so that's our bound, and we can really okay. So we're going to have do the same thing. So that's just a little. This is just a little interlude. We're going to do the same thing. We've got our sum m equals n, and then we've got our sum m not equal to n. From m equals n, that's just going to give us t. It's going to give us big O of t times the LT norm squared of our coefficients in a very easy way. And then from the sum m not equal to n, we have to work a little bit harder. But the diagonal term is okay. Well, so maybe if I draw the picture here. So now we're getting like things near the diagonal. We're kind of getting like maybe a shade, like a kind of the shaded region. M and n have to be quite close. So we're getting a very narrow band around the diagonal. Whereas before we just had these other parallel lines that were quite far, maybe in the Archimedean sense, but close mod Q. Okay, so from m not equal to n, we can do the exact same trick. So we're going to have, let's just look at let's look at am squared, and then we're going to look at n minus m, or okay, let's just look at n. And then we've got our t, and then we'll just put in this bound, w hat of t log n over m. And then let's just, by symmetry, look at n bigger than m. So if n equals m plus h, then w hat of t log, or just, so the log n over m is log m plus h over m, which is log of 1 plus h over m, and then this is at most h over m. And so so the bound we'll get for the inner sum will be at most sum over h greater than or equal to 1. And then we can put in our bound on w hat. So this will be 1 plus t h over m to the minus 2024, which we can bound by, so this is a sum, we can sum h up to m over t plus, and then we've got the tail h less, or h bigger than m over t, and then for that we can just say m squared over t squared h squared, and then either way you get the bound m over t. And so, so the sum over m and n, m not, so the sum of the off diagonals using symmetry, like all these terms are basically the same, like choosing n bigger than m or vice versa doesn't, you end up with the same bound in the end. We're going to get what am I trying to write? I mean, it's so this thing is just going to give us t and then sum over m, that's our outer variable. And then the inner sum was just my capital M became an N somehow. That should be capital N. There's no capital M in this one. Okay, we'll fix it. So the t's cancel, and you just get n times the LT norm squared of your coefficients. And that's the other term in the bound. So we always have these two terms, one from the diagonal and one from the off diagonals. So okay, so that's these two elementary bounds on these bilinear forms. And so now let's use them to prove something about moments. So, okay, so as a corollary, we can prove a second moment bound on Dirichlet L functions. That this is bounded by Q log Q. And then similarly, we can get a second moment on the Riemann zeta function. That this is bounded by T log T. Okay. So, I mean, it's a proof. I mean, it's a corollary, but it does require some proof. But we've developed the machinery we need. The machinery is the approximate functional equation and these flexible bounds. So let's prove one. Let's start with the Dirichlet L function version. So here's what I'm going to do. So let's take a subsum. So I'm going to put a plus here, where the plus is going to refer to even primitive characters. And all right. And then for primitive even characters, I have the approximate functional equation of the form some chi of n over square root of n. I've got this v 1/2 n over square root of q. Oh, I forgot to mention the x, but okay, let's write down what we've got here. So I'm going to choose x equals 1. Oops. So in the approximate functional equation, you can pick this parameter x. We have chi bar of n over square root of n, and then v 1/2, also n over root q, absolute value squared of this thing. So this is just writing in the L function, writing in the approximate functional equation for the L function. So why did I want primitive characters? So I need primitive characters because in the approximate functional equation, we had to assume that we have like an honest to goodness L function that satisfies the functional equation of our prescribed shape, and so that requires that we have primitive characters. So if our character is not primitive, then some of the Euler factors can be wrong, and then the functional equation is off from that. So we have to restrict to primitive characters for that reason. And then why did I want even characters? So I could restrict to even or odd characters, and we'll basically get the same thing. But this v function, which is we're evaluating it at a half because we're trying to bound the moment at a half. But the v function depends on the parity. So so this depends on parity of chi. Now it's not a big deal, but it's just if you want to write a formula that if you want your v to not depend on chi, and as long as I restrict first to even characters or to odd characters, then that will be ensured. So the reason is just from, if you remember back from the gamma factors for Dirichlet L functions, when we did our examples, the gamma factor, we have like this +1 shift for odd characters. And so the gamma factors depend on that, and then the gamma factors are baked into the definition of V. So, okay, anyway, so we've got that. So now I want to use this simple inequality like a plus b squared as at most 2a squared plus 2b squared. That is just to kind of get rid of any cross terms. So you could square this out, and then you'll have to deal with absolute value of a squared, absolute value of b squared, and then cross terms with a and b. But if you just want an upper bound, you can completely avoid the cross term problem using this simple inequality. And then so A, so this first term is going to be A. This first sum is A. This second sum is B. And A and B in absolute value are the same thing. So so doubling it up again, we're going to get 4, factor of 4, and then we still have the sum over even primitive characters. And then now it's a little bit simpler because we can just look at the first term. Now, once I have this, I can then freely drop the condition that chi is primitive and even. Okay. So this is where once you have an expression, then you can by positivity you can overextend things. So great. I wanted to go, I mean, okay, I forgot to mention this x factor. So here I'm choosing x equals 1. So if you remember, like x was something to make the two terms less symmetric. So we had an x like kind of in the numerator of the argument of v on one side and in the denominator on the other side. So it's kind of a way to make one of the sums longer than the other. In this case, these two sums are essentially the same thing, the way we're setting this up. So there's no gain from choosing choosing x different from 1. But for some applications, you might want to choose x and differently than 1 to balance the difficulty between the two terms. So the cases where I've seen this happen occur when the root number is difficult to handle. So like if you want asymptotics, then you have to study cross terms, and so you might have to study the average of A, like sort of A times B. And so if you have A times B, you'll have a chi of n, you'll have a chi bar of m, and you'll also have this epsilon factor, and you have to average that over your family. And that can cause some problems. And so by choosing x, you might be able to kind of diminish how difficult that part is and make the other part easier. Anyway, so that's just a side remark because I didn't want to forget that. Okay, so now let's go back to continue the proof. So we've got a few different ways to proceed. So just let me recall v1/2 of x, or just v of x is bounded by, oh, did I mention this? Oh, maybe I forgot to mention this. I think we forgot to mention our bounds on v, didn't we? Yeah, okay, yeah, I skipped that part. So, okay, we need bounds on v. Okay, yeah, I've got it in my notes and I forgot to cover it. So, all right, so like maybe a little interlude here. Maybe I'll put this in a different color. Oops. We need bounds on v. So, okay, so let's fill in that gap now. So the result that I want to claim is that if you take so you take your v function, you take the jth derivative of it, and you multiply by y to the j, then this is bounded by 1 plus y over the conductor to negative any power you like, negative a million power. This is as y goes up to infinity. I mean, this is just a bound. So for the case that we care about, I mean, so maybe we'll verify this in this special case. I mean, the idea is, so first of all, think about j equals 0. So at j equals 0, what you have is v sub s of y is this integral. You've got your gamma factor. So you've got y to the minus u. You've got your gamma factor. ratio of gamma factors. One of them is at U, the other is at S. I think we divide by S, G of U over U du. And let's choose, okay, so let's choose G to be something like exponential of U squared. So this this actually has rapid decay for U equals like sigma plus IT, sigma in some compact set. So if you look in a vertical strip, this thing has rapid decay in T. So on horizontal strips, it blows up quite fast, as we know. But if you rotate by 90 degrees, it has rapid decay. So you can do something like this. This is just to help secure convergence. So let's just prove it for this. Like we have this we have this huge class of functions, capital G, that we can choose in the approximate functional equation. So we should just choose one to make our lives as easy as possible. So let's choose that. If S is just fixed, so like if you fix S, like S equals a half, then this thing is really, you don't even need to do this. You could just choose G of U to be constant function 1, and you've got V 1/2 of Y is this pretty simple function, y to the minus u, and then it's just this, I mean, I don't know why I'm writing this again, but so if you fix S equals a half, then what you can do is shift contours to the line real part of u is equal to A, and then you bound with absolute values. And you just use the triangle inequality. So you shift the line to the line real part of u equals A. Your y to the minus u part, that's y to the minus A, and absolute value. You have to, and then for the stuff that's left over, it's just an integral in u, and it just converges because, I mean, first of all, a gamma function has exponential decay in the imaginary direction. And then for this choice of g, this is just extra exponential decay, which we didn't even need. We could have chosen g of u to be the constant function 1, and it would have been a perfectly fine function. So that shows you this bound y to the minus A. And then if y is small, what we should do is shift left. So this is for y bigger than, maybe for y bigger than 1, you do this. For y less than 1, then instead shift to some other line like real part of u equals, I don't know, minus a quarter or something like that. And then you'll hit a pole at 0, and the function is just, so it'll be actually 1 plus big O of like y to the quarter. But I think for what I'm using, I don't even need that. I just want to know that it's big O of 1. Okay, maybe I will want to use this. So V 1/2 of y will be 1 plus big O of y to the quarter for y going to 0 from the right. So this V function is quite nice. So it's approximately 1 for y small, and then it has rapid decay for y going off to infinity. Where things get a little bit trickier in this proposition is if the gamma factors are varying in some way. So if you want S to vary, then this is a little more complicated, but you have to use Stirling's formula, and then G can help everything converge when you use Stirling. So you can still get this bound. Okay, so I explained this when J is 0. If you take higher derivatives, so if you differentiate, just imagine what happens if you differentiate in y once in this formula. If you just bring the derivative inside the integral, you'll bring down a negative u, and you'll divide by a y, right? So you'll just use, so to do the derivative, maybe I'll write this in orange. So if you do d dy of y to the minus u, this is negative u, y to the minus u minus 1. And so if I take the operator where I multiply by y, then all I've done is multiply by negative u. And so if you do the same process where all you've done is multiply by negative u, you still get the rapid decay at infinity, and then at 0, you actually have kind of canceled out the pole at u equals 0, so you don't even pick up a pole there. Anyway, so for the case of Dirichlet functions at a half, which is what we're doing right now, this proposition is quite simple to prove, and yeah, and so if you want to see the full proof with all the gamma factors, go look in Ivanitz and Kowalski, because it's a somewhat involved Stirling's formula proof. Okay, so that's our interlude on V. Okay, so I forgot to do that, but now we're back. So okay, so now we're back to our sum. We need to sum over chi mod q of this sum. And so now that we know this proposition, this is basically going to say that v1 half has rapid decay. So so the main part is n going up to square root of q, and then we also have maybe the tail where n is bigger than root q. So the thing that we're bounding. So the thing that we're bounding, our second moment of Dirichlet functions, and with a plus, so chi mod q, primitive characters, even characters, L of a half chi squared is bounded by q, and then we'll do the same thing. So let's sum n up to root q, chi of n over root n. We've got our v function, and then squared, and then we'll have the tail. So we'll do our same trick of how to separate these. So for the first piece, you just use our mean value theorem that we proved. So for the first part, we get q, we get root q plus q times the L2 norm squared of the coefficients, which is v of n over root q quantity squared over n. And so the v is bounded by a constant, and so this is just bounded by, this shouldn't have been the q. Okay, there we go. What did I do wrong? No, there's no q. This is sum over chi. Okay. When we do the sum over chi, we get a q from the orthogonality. Okay, so v of x is bounded by a constant, like big O of 1. So this is like the harmonic series, so that you just get q log q. Okay, so what we could do is chop it off at a different place. Like we could have chopped it off at, like there's a lot of room. Like we could have chopped it off at q. So the chop off point or the truncation point here. I chose it to be square root of q, but to sort of make a point. We could have made it bigger without affecting the bound because we already have this plus q term. So we could have chopped it off at q instead of root q, and then that would have been fine too. And then the tail then would have been for n bigger than q, and then the tail is actually extremely small because we're way off in the range where v has rapid decay. So we could have done that. Might have been a little simpler, but I wanted to chop it off basically at the point where we should be chopping it off, which is the square root of q, and then I want to bound the tail. So the tail we can do. I mean, there are different things, but maybe the most natural thing I think is just summation by parts. So let's let w of n be this v of n over square root of q. So then what we want is, okay. So this is a smooth function, and then we have summation by part. Okay, so summation by parts. So the way I like to do summation by parts is just, it's always the integral of the derivative. W has rapid decay at infinity, so I can integrate up to infinity and like that boundary term disappears. And so the thing I want to bound is the sum over chi mod q. So sum over n bigger than root q, chi of n over square root of n, and then as my w of n, and then my w of n I'm writing as integral minus the integral n to infinity w prime of t dt squared. So this is my tail term, and I'm just using summation by parts. So this is a useful technique, so I just wanted to show it because it's even if we could get around it this time, there are other places where we can't. So now when I switch the order of integration and summation, now the lowest n ever gets to is root q, so the lowest t ever gets to is root q. I've got w prime of t, and then minus sign. Now I've got n going between root q and t. And chi of n over root n dt squared. Okay, and then now I'm going to use Cauchy on this to square this out, and then it'll be pretty well set up to use this mean value result that we proved, this proposition. So okay, so Cauchy says, so I want to use like yeah, I want to take the integral to the outside and keep the sum on the inside. So I guess okay, so this should be bounded by square root of q to infinity, integral w prime of u du at the absolute values as one factor, and then the other factor will be root q to infinity, another w prime of, let's say, t, and then this L2 norm, or this, sorry, this sum chi of n over root n squared dt. So, okay. So I claim this thing is big O of 1. This integral over u, I claim that that's big O of 1. We'll circle back on that. And but so if so, then this should be bounded by integral root q to infinity, absolute value w prime of t. And then now it's just to put everything together or put it in the right place to stare at it. It should look like this. So now this thing is in the curly brackets is we can use our proposition for. So this is bounded by q plus t times the sum 1 over n d, and then I've got my w prime of t dt, and this sum is big O of log t, and so then now I claim that integral root q to infinity. Let's see. So I guess I want log t absolute value w prime of t. I'm going to claim that that's big O of log q. And then I also want to claim that if I integrate from root q to infinity, t times the absolute value of w prime of t dt. Oh, also with the log t. That's big O of q log q. Actually, it should be root q log q. So basically, this is saying like this is why we're going to get q log q. I'm working a little bit harder to do this. I'm sort of doing this the hard way because it's going to generalize to cases where we can't quite chop it off at exactly where, or let's see, where we can't cut it off in such a simple way. So right, so to show these claims, oh, and the other claim was just the integral w prime is big O of 1. So there are three things we want to prove are this. Okay, and these are all pretty much the same sort of if you can do one, you can do all three. So remember, w of x was v of x over root q. So this implies that w prime of x is 1 over root q v prime x over root q. And we have bounds on this. So so w prime of x is bounded by, 1 over root q. So v prime, I guess we can multiply it through by x. And yeah, and so then this will be like, well, okay. So we have different bounds. So this is bounded by like 1 plus x over root q to the minus 100. We'll have x, w prime of x. So this is also bounded by 1 plus x over root q to the minus 100. Oh, also the first one is 1 over root q. Yeah, I forgot the root q, etc. So for example, the first one is actually small. Did I do this right? That looks okay to me. Okay, should we just pick one or do the hardest? Let's just do the first one. So just as an example of one of the three. So we want to integrate root q to infinity, log t, w prime of t, dt. So this is bounded by 1 over root q, integral root q to infinity, log t, 1 plus t over root q to the minus 2, let's say. Dt. So you can change variables. T goes to root q times t. We'll get integral from 1 to infinity. We'll get less than or equal to log of q plus log of t. And then 1 plus t to the minus 2 dt. And then integral log t over t squared just converges, you just get a number. So this is big O log t or log q, which is what we wanted, right? Yeah. So they're all basically the same thing. Okay. So that's our second moment bound for Dirichlet L functions. Maybe I should say, so the proof that I gave, one of the reasons why I worked hard to do it the way that I did it was that we can actually do the same proof, the same method of proof to get a fourth moment bound. So we can get a bound on the fourth moment of Dirichlet L functions, and this will be bounded by q log of q. So I guess this is to the fourth by same overall method. And so this is a yeah, and so how's that? It's basically the same thing. We're gonna have what we're gonna end up with as a sum over, just to kind of sketch this out in a very brief detail. We'll end up with something like the divisor function of n times chi of n over square root of n, and then now we'll have v of n over q. So now, so essentially like n sort of goes up to q now, because we have a fourth moment. So in a way, what I'm doing is like, it's like a second moment of the Dirichlet L function squared. So L of a half, or L of s chi quantity squared is the sort of the same sort of looking L function, except multiplied by the divisor function. And if the conductor of the L function squared is the square of the conductor of the L function, and so now this has conductor q squared, and so we'll get n up to q instead of n up to root q. And then now this is a little more delicate to get the exact kind of sharp bound that we want, because now the length is essentially q, and then the number of characters is also q. So our bound is like q plus the length. And so it's a little trickier, but we can still do this summation by parts argument and push it through. And then the main thing that we need is that sum n up to x, divisor function of n squared over n is bounded by x, or sorry, there's no x. So this should be bounded by log of x to the fourth, I guess.
You want one with a cube, no?
With a cube?
Yeah, because it's 4 and you get.
But I think you get one more because it's the harmonic series. If I'm not mistaken. So you're right. So I think if you had n up to x, divisor function of n squared without the 1 over n, then you get x log of x cubed. But then when you have the 1 over n, you get an extra log. Just like, if there's no divisor function, maybe I'll put this just in red or something. So if you have n up to x, 1,
Yeah,
right, this is like x, but if you just have 1 over n, it's log of x. So the 1 over n gives you an extra pole. That's how I always thinking about it.
correct.
Yeah.
I was thinking of the sharp upper bound with log q cube, but
Log q cubed.
for the fourth moment.
Isn't it log to the fourth though? It's just like the zeta function.
Okay.
Right? Like the bound should be okay. I mean, I'm getting a little okay. So the conjecture is that the zeta function, the 2kth moment of that is some constant depending on t, and then it's log t to the k squared.
Yeah, correct.
Yeah, so when k is 2, you get log t to the fourth. Yeah. I wasn't going to talk much about these conjectures, although I could easily give 4 lectures just about all these conjectures and everything. Let's see. Yeah, okay. So just going back, so you can get the sharp bound on the fourth moment of Dirichlet functions using this trick. It's not if you don't care about like the right power of log of x, it's very easy to get like q to the 1 plus epsilon for the fourth moment, because once you can truncate the sum at q to the 1 plus epsilon without any trouble, and the tail will be very, very small, and then you'll get a bound q to the 1 plus epsilon. But if you just really want the q log q to the fourth, then you have to work a bit harder. Okay. And then the t integral is, so the second moment of zeta squared dt less than t log t is similar. So I don't think I want to go through the proof of that. And then the method will also get a good upper bound on the fourth moment of zeta. So, all right. So one of the things I did here was so I used this very simple inequality that this is at most 2 absolute value of a squared plus 2 absolute value of b squared. And what that does is, so it's I don't know if this is deceptive or not, but if you're willing to use this trick, it really makes your life a lot easier. But the penalty is that you cannot get an asymptotic formula. This is really like a one-sided inequality. And so this, if you, as soon as you start using these kinds of inequalities, you give up on getting an asymptotic formula. So, um, so it is possible to prove an asymptotic formula for this second moment of Dirichlet functions. Um, so this should be asymptotic to q log q. I might be assuming q is a prime here. Yeah, or maybe I have to multiply by q over phi of q. Yeah, so this should be, I guess maybe this is asymptotic to phi of q log q. This is true. And maybe I want, okay, maybe really what I should do is primitive characters, and then phi star of q would be the number of primitive characters, but never mind. I mean, these are like side comments. But so it is possible to get an asymptotic formula for the second moment of Dirichlet functions, but you can't use the same method of proof. You have to work harder. And so here's one way to do this. So if you, okay, so maybe a kind of I think just for purposes of time, maybe I won't do this, but you might for yourselves try it with the approximate functional equation. But and then what you would have to do is deal with the cross terms. I guess I call them the cross terms. So one of them would be a b, so a b bar, and then you also have a bar b. Okay, so you have to deal with those cross terms, and then the root number enters into the picture if you do it that way, because b has a root number, a does not have a root number, and you have to, and that will modify the how the proof goes. And you run into some annoying issues, but maybe I won't, just because I'm running low on time, maybe I won't mention what issues you run into. But there's a workaround that I like, which is that you can use an approximate functional equation for the L function L of a half chi, L of a half chi bar, which you view as a degree 2 L function. So if you have if you multiply two L functions together, you get another L function. It still satisfies a functional equation, and has gamma factors with a product, all that good stuff. But now this would just be like a degree 2 L function. And the gain on this is that this has this is sort of a self-dual L function where there's basically the root number is +1. And it's because the root number for chi times the root number for chi bar, the product has to be +1, because that's the same as if you applied the functional equation twice. If you did it once, you get epsilon. If you do it again, you get epsilon of chi bar, and you're back to where you started from. So the root number of this product of L functions is +1. And so what that's going to mean is that if you apply the approximate functional equation to this L function, you're going to get the following thing. And then you'll have some function v. Now the conductor is q, I guess the conductor is q squared instead of q. And so the square root of the conductor is q instead of square root of q. So the product mn goes up to q. This 2 in front is from the symmetry, so both terms are the same. So I can just double it up. And then now you're free to apply. So I think what I wanted to do is just do this for, let's take q to be a prime. And let's just take the sum over odd characters. The reason why I chose odd characters is that every odd character mod of prime is automatically primitive, because mod of prime, you have the trivial character, and then everything else is primitive, and the trivial character is even. So if you restrict to odd characters, everything is primitive for free. And so what you'll get is that you'll sum over chi mod p. I'll put a minus sign to represent the odd characters. And then I want to sum over, yeah. And so, and then to detect odd characters, you can do this trick. Okay, you take 1 minus chi of -1. Right, so if chi of -1 is +1, this is 0, and if it's -1, then if chi of -1 is -1, then this thing I wrote is 1. Okay, and then I plug in my formula for the L function squared. And now Q is P. And now you can just use orthogonality of characters. It's quite nice. So the 2 and the 2's cancel. So I'll get a double sum. I'll get P minus 1 from the number of Dirichlet characters. So the first sum without the chi of -1, this will tell me that M is congruent to N mod P. 1 over root Mn, V of Mn over P. And then the part with the chi of -1 term, that's M congruent to -N mod P. 1 over root Mn, V of Mn over P. Great. So now we're in business. This is pretty easy to handle now. So for this part, when M is congruent to N, you've got the diagonal term. And that leads you to P minus 1, sum over N, 1 over N, V of N squared over P. And a little bit of work shows that this is asymptotic to P log P. From these terms where M is congruent to N, but M is not equal to N, then you don't get very much from this, because let's say, let's just take M bigger than N. So let's write M equals N plus PL, where L is greater than or equal to 1. So these terms you get sum over N, sum over L, 1. Okay, so you've got a big, I just want to bound these. So we'll get a P square root of N, square root of N plus PL, and then V of or absolute value V N plus PL over P. So basically, like, this is already, we're already kind of in the tail like this. So like this is V of like something plus NL over P, and the something is positive. So this is a positive quantity. And so this is basically saying that NL goes up to P. So, or sorry, NL, but there's the P's canceled. So basically NL goes up to like 1. Or you think of maybe you think of NL as big O of 1. Which means that N and L are both big O of 1 here. And so there's almost like nothing left in the sum at all. And so this is just bounded by square root of P. Or if you maybe to write it in a little bit more detail. So you've got a P, you have your sum over N, you have your sum over L, 1 over square root of N PL. So just drop the N part in that square root. NL is less than 1. So this is just bounded by a square root of P. So this is like massively smaller than the main term. The main term was size P log P. So now this is size square root of P. And then similarly, the sum over M congruent to -N mod P. Whoops, what happened? Okay, M congruent to -N mod P, 1 over root Mn times the P. I think what do we want to say here? So I think we get the same bound that we can say this is bounded by root P, because if N is less than or equal to P over 2, then m is positive, so m equals negative n plus PL, where L is greater than or equal to 1. And like the negative, like the fact that you have a minus sign doesn't really hurt you very much because you're subtracting off at most P over 2 and M is at least P. And then so you get the same bound here. And then on the other hand, if N is bigger than P over 2, then basically this is saying that M is also at most P over 2 because the product, I mean, actually, M times N basically goes up to P. So, so M will have to be very small. So if N is actually bigger than P over 2, then M is basically big O of 1. So, great. And so I think what we've shown is that if you sum over chi odd mod P, L of a half chi squared, this is equal to P log P plus big O of P to the 1/2. So we can get an asymptotic formula, and it uses this trick of the approximate functional equation for the product of the two L functions to get rid of the root number, which is pretty convenient. It comes up a lot in some different papers. So, all right. And then just as a remark, it's pretty easy to show, even easier to show if you sum over chi mod P, L of a half chi, that's asymptotic to P. So we can get a good asymptotic for the first moment, not without any absolute values. Absolute values would make this hard, but you can do the same thing for the L function itself. I'll just leave that as an exercise for you if you want to test this. Just plug in the approximate functional equation, and the dust will settle, and you don't have to work very hard. But this is a good exercise if you've never played around with the approximate functional equation before. But then I'll just finish with this following corollary, which is maybe we can think of as an application of moments. So I've been talking about moments, but I haven't really said much about why we care or what they're good for. So one thing that they're good for is we can use them to prove non-vanishing of L functions. So let n of chi equal the number of chi mod P such that L of a half chi is not equal to 0. So it's the number of characters mod P. Oh, I guess there should be n of P, not n of chi. Okay, then n of P is bounded from below by P over log P. And you can get explicit constants here. Maybe it's just basically P over log P without any constant at all. And there's a very standard proof that almost fits into one line. And that'll be the last thing I tell you about. So you combine the first moment and the second moment as follows. So we have that P is asymptotic to our first moment. We can put in absolute values for free because the average is positive. Then what do we do? So we say this is the sum over chi mod P, and then we just multiply by, I'll call it delta sub chi. So delta sub chi is equal to, so delta chi is equal to 1 if the L function is not 0, and it's 0 if the L function is 0. Okay. And then now you just use Cauchy-Schwarz to say this is bounded by chi mod P, delta chi absolute value squared to the 1/2, and then sum over chi mod P L function squared to the 1/2. So this is exactly, so this first thing is n of P to the 1/2. Right? It's just counting the number of chi's where delta is not equal to 0. It's the same as counting the number of chi's where delta is equal to 1. And then as times our second moment, and our second moment, we actually got an asymptotic formula for it, but it was easier actually to get the upper bound. So we can get the upper bound of p log p to the 1/2. And then if you solve for n of p, we get a lower bound on n of p. So n of p is bounded by p over log p. So not very many of these L functions can equal 0 at 1/2. And in general, if you have a family of L functions and you can understand the first and the second moments of them, then you can do this kind of Cauchy-Schwarz argument to get a non-vanishing result for the L functions. One thing I can say is that you can't really improve on this because it's consistent with L of 1/2 chi being size, let's see here. So log of p for p over log p chi's and 0 for the rest. So imagine you just say the L functions are equal to 0 for all but p over log p chi's, and then for those, let's just say it's equal to log of p. So the first moment in this crazy model, so the first moment would be sum over chi mod p log p, but it's the chi's where the L function doesn't vanish. And then there's p over log of p of those. So this would be p over log of p times log of p, which is size p. That's what we proved, or what I claimed was an exercise, is to prove that the first moment is size p. And then for the second moment, we'd have chi mod p, where the L function doesn't vanish. And then we'd have log of p quantity squared, right? Because it's size log p, but then it's a second moment, so it's log squared p. And then this would be p over log of p times log squared of p. And that's p log p. And that's what we proved as the asymptotic for this thing. So if the only information you have about your L functions are the first and second moments, then we can't conclude anything stronger than this corollary, because the corollary is consistent with these two models, which are consistent with the first and second moments that we developed. And so next time I'll talk a little bit about how we can improve on this with some extra information and other sorts of things. So okay, I'll stop with this and let you go enjoy the rest of your evening.
Do you have questions for Matt? Any questions?
I maybe have a remark about the +1 issue. I also don't know a name for it, but it's almost what computer scientists call the fence post problem. Like if you want to put a fence every 3 feet for 30 feet, how many fence posts do you need? And it's like one more than dividing the length by the distance between them.
Yeah. Yeah,
So
I don't know if the
we
number
can
theorists know this terminology, so I don't know if it would catch on, but I think we need a name for it.
Yeah.
There are all these places where you think you've proved some pretty amazing results if you just drop this +1. So it's easy. Yeah. Anyway. So it's really important, but it's deceptive. It's deceptive, and yeah, it would be good to have a name for it. So we have like a name for our enemy.
Any question or comment? So if not, we can thank Matt again.